Oh man, that computer is wonky. Not good. All right, any other questions? Yes, ma'am.
Okay, 768 says, which of the following does not exist naturally in diatomic molecules with their own species?
What are the answers?
Hydrogen, sulfur, nitrogen, chlorine, oxygen.
Okay, I can answer this in one word. Uncle Griff.
Oh.
Do you remember that? Okay, so which guys are a member of this family here, Uncle Griff? Hydrogen? Yes. Oxygen? Yes. Chlorine? Yes. Nitrogen? Yes. Sulfur? No. So sulfur would be the guy. Which of the following did not occur naturally as a diatomic element?
What's in the bag?
Toys that we're going to use today. Yes, sir. Uncle Griff is a, what do you call this, an acronym? An acronym that we use to try to remember the 7 elements in the table that occur as homonuclear diatomic structures. Okay, and that means they occur as 2s. So hydrogen is always found as H2, oxygen as O2, nitrogen N2, chlorine Cl2, and so forth. Those 7 are the ones that exist that way. And so this is just a cheap, easy way for us to remember the 7. Okay? Anything else? In the element who? 7N?
Yes.
How many valence electrons? Oh, this is so easy. Okay? I'm going to go to the periodic table and find N, and I'm going to look at the group number that it's in. And if the group number is a Roman numeral, that's the answer. If it's a cardinal number, I take the last digit, and it's 5.
Did you not call what you put on?
Okay? Any others? I'm on a roll. I've got them all right.
Hey, I got
Yeah, you
it
go.
was on the practice, and it said something about which scientists, something with the energy level model. Was it Rutherford or?
The energy shells,
You say energy level model.
energy level model. I'm going with Bohr.
Or?
Yeah. Because what did Rutherford do? Rutherford was the nucleus, and he said the electrons were out there. He didn't know anything about where they were or how they were structured.
And the Bohr model.
But Bohr
has actual
drew the energy shells, the energy levels. So I'm going with Bohr.
I have a
You have another one?
yeah. So I kind of get the difference between polar and non-polar, but like the way the book describes it, it don't kind of make sense.
Well, then you came to the right class because we're doing that today.
Okay.
Okay? Anything else? No, good. Okay, so got the tactful way instructors cut you off. So we've done a little bit of dot structures. And we made the impression, I think, that some of them are pretty straightforward. But actually some of them can be a little tougher to do. And so what we have is a stepwise procedure that becomes almost foolproof for us. So I thought what we do today is to give you the steps and go over a couple of examples, let you try one, and see how you do with it. So these are the steps that we follow for writing correct electron dot structures. Number 1, calculate the total number of valence electrons.
Just hold. Can you repeat that, please?
Calculate the total number of valence electrons. And so you look at each atom, figure out what its valence electrons are. Where would you get that from?
The
Periodic table. And then if it has a charge, you have to add or subtract electrons. If it's a -2 charge, that means what? It has 2 extra electrons in addition to the total that you got. All right, so you find that total number of electrons. Step 2, find a central atom. Bond all the other atoms to the central atom. Now, what does that mean?
That's step 3 or?
No, that's 2.
Hold on, you
Central
said-
atom is sort of the strange guy. Okay? He'll be the single atom if he's there alone. He will be a carbon if there's a carbon present. There'll always be a carbon. Okay?
Can you repeat the question? You said find the central atom.
Find the central atom. And then bond all the other atoms to the central atom with a single bond.
So you meaning like if it's like I don't even know if it's like if you got like a carbon and 2 phosphorus, you would do
Carbon.
the carbon would be the central.
Yes.
So will it ever be an incident where it's like 3 elements and we wouldn't know what is the central?
No. If there's 3 elements, you'll know what the central is. You're going to know. Okay? You're going to train yourself to know. So, number 2, we're going to find a central atom. We're going to bond other atoms to the central atom with a single bond.
Carbon will always be.
If carbon's present, it's always the central atom. Okay? Hydrogen is never the central atom. Because how could he be? He can only bond once. Right? Oxygen is usually not, unless there's nothing else around to pick on. All right, I'll give you the steps and then we'll go through them again with an example. 3, we're going to add non-bonding pairs to the atoms that are not the central atom to complete their octet.
Whoa.
We're going to add electrons to the non-central atom.
That's
You
not,
just said-
that's not what you just said.
You said add non-bonded pairs.
Well, that's what I'm saying. We're going to add electrons to the non-central atom to complete their octet, and they will be non-bonding pairs when we do this.
You confused me. So you
Yeah, because I
said
started writing one
add
thing and then you just.
electrons.
Okay, these rules are in your book. On page 115, although mine might be a little bit different.
Add
I
electrons.
think it's 115. Is there a rule on it?
She's saying that, like this. Yeah, but I started writing it one way.
You said add electrons to the atom.
Try 118,
118. That's what I think I said.
I think. 118.
118 rules?
No, no, that's not it.
All right, forget that. I'll put them on the board.
You said add electrons.
I got add electrons to the,
What are we adding electrons?
I'm guessing the central
To
atom.
the non.
The non-central atom.
I think it's the bottom of 115.
It is 115.
Yeah, I think it's the bottom of 115.
Oh, no, we don't want it.
All right, in any case, here we go. Look at rule number 1. It says calculate the total number of valence electrons.
Oh, I have that printed out right there.
Do you have that on your page?
Yes, see that?
Apparently I do.
All right.
2, write the chemical symbols of the atoms of the molecule in the order in which they are bonded to one another and place a single covalent bond to the electron. That means find the central atom, okay, and put the other guys around the central atom. Let's do an example now. All right. Let's do SO2. Okay, while we go through this. So, what's step number 1? Okay, here's what I heard. Womp, 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 womp. I feel like I'm in a Peanuts cartoon. All right, count the number of valence electrons. Sulfur.
5. 6.
Oxygen.
7.
But there's 2 of them. Total, I've got 18 electrons to play with.
Wait a minute.
Okay?
Okay.
Good? We can count?
Mm-hmm.
So, If you had to pick a central atom here, what do you think you're looking at?
Sulfur?
So,
Sulfur. He's the single guy, the weirder looking of the two. Let's make sulfur our central atom.
Why?
Step 2 says, because that's what God said. Sulfur is central atom. Step 2 says, put the other atoms bonded to the central atom with a single bond. Now what's a single bond?
One line.
A pair of electrons, okay? So I'm going to put a pair of electrons here with an oxygen and a pair of electrons here with an oxygen. Okay? I have bonded my non-central atoms to my central atom with a single bond, which is a pair of electrons. Now how many electrons have I used?
4.
So I have 14 left at this point. Okay, what's the next step?
Make an octet.
Add non-bonding electrons to the outer atoms so that they have an octet of electrons. Now if it's hydrogen, remember hydrogen doesn't get an octet, it only gets a duet. And it's probably done already. So, who are we playing with here in this step? The oxygens. And so this oxygen would need 6. So I'm going to do 1, 2, 3, 4, 5, 6. This oxygen, the same. So 1, 2, 3, 4, 5, 6. So how many have I used total in this exercise?
12.
12. So I'm going to subtract 12 here, and I have 2 left. Okay? Next step, number 4. Place any remaining electrons on the central atom.
so bottom 11. So,
No, I'm going to put a pair.
prepare, okay, keep it with me.
Okay? So I'm just following the steps. Number 5. If there are not enough electrons, and I'm done with electrons now, right? If there are not enough electrons to give the central atom octet, then you've got to look toward multiple bonding. And how do we multiple bond? We take a pair, a non-bonding pair, from one of the guys. Who's your favorite today, left or right?
Right.
Left, I heard first. So we're going to take a pair from there and multiple bond. That means they're going to share with both.
Huh?
Why?
Because it's a rule. Okay? I'm trying to achieve a valid dot structure, and these steps will get me to a valid dot structure if I follow them step by step. So it says that if I don't have an octet on the central atom, and look, I don't. The central atom has 6. Then consider multiple bonding by moving a pair of non-bonding over to where they become bonding.
So you do the same thing on the right.
I could have. I didn't, but I could have. Should I? Well, how many electrons does the sulfur have now?
Still.
8.
Yeah.
How many does this oxygen have?
7.
8. This oxygen. I've got a dot structure where everybody's got an octet. What could be nicer?
So how does sulfur have 8? Are you using the other 2 with oxygen? Those 2 are there?
It's a multiple bond.
You look at all the electrons that are immediately on the sulfur. If it's a double bond, then you count all of them. Yes.
And I just wanted that, I know we got the 6 from sulfur.
Right.
Up there, and then the 12.
Oxygen has 6 also, but there's 2 oxygens. 2 6 is 12. Yeah. So a total of 18. Yes, sir.
So every atom is supposed to have 6.
No. Every atom is supposed to have 8. It's an octet rule. We want every atom to have 8 in our structure.
So that's the finish.
This?
You know,
Yes.
so when we had oxygen had 8 and most of the oxygen had step 2 you had before you did that. That's wrong.
Yes. Because the oxygens both have 8, but the sulfur only has 6.
How do you differentiate on the periodic table transition metals?
Transition metal is this block of elements right here.
So when you're naming,
When you're naming chemical compounds and it's a transition metal,
yeah,
you should put a
obviously
Roman
use the
numeral,
Roman numeral.
unless it's zinc or silver.
Okay, so zinc and silver.
They're an exception.
Okay.
And silver,
All right, should we try another?
Please.
pretty.
Because I always don't know where it's from.
Yeah.
Is it against the rules for either oxygen to take more than one electron?
To just do what with one electron?
Because we took two from the left side.
Yeah.
Of the left oxygen, is it against rule if, let's say, the left and the right oxygen gave one, or is that not possible?
We generally give them in pairs. I understand what you're saying, have each one of them give one. We generally give them in pairs. Now, in truth, this is a paper exercise. Is this what really nature does? Nature does something much more complicated, which I don't think we want to go through yet. Okay. All right, let's try this one. SO3. Step 1, number of valence electrons. Sulfur has oxygen, total 18. Total number of 24 electrons. Who do you think is the central atom? Sulfur.
Is it because sulfur is the only one? That, I mean, it
Sulfur is
doesn't
the
have
single guy.
Yeah.
Yeah, pick on the single guy. Nice. All right, what's the next step?
Draw sulfur.
Non-bonding acid.
Let's put those oxygens around the central atom with a single bond. That's a pair of electrons.
You don't have enough.
How many electrons did I use?
6.
So let me subtract that. I have 18 left. Okay, and
Outer.
now I'm going to fill the outer octets, right? So I'm doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
What's there?
And now we have to make
I have 0 electrons left. Okay, does my central atom have 8?
Share.
Uh-oh, double bond. Who's your favorite today? Left, right, or top?
Top.
Top. In truth, it doesn't matter which one you pick. Yes,
So why did you take 2 electrons from the top?
they told me to. I have to take them from one of the oxygens, okay, because my sulfur currently does not have an octet. It has 6, and I have no more electrons to play with. So in order to make an octet here, I have to multiple bond. Now, in truth, it doesn't matter which one I use. We just decided to use the top, and so we get this. Then you, yes, and then you're just done.
You always try to get 8.
Yeah.
Unless it's hydrogen, then there's only 2. But otherwise, it's 8. No,
We don't have a.
I'm sorry?
I'm gonna ask, so it's just like the middle term that has to have 8 or all of them have to
They all have to have 8.
have 8? Okay.
All right? You want a solo?
Yes, please.
Yes, ma'am. Can I do one with hydrogen? How about I let you try one with hydrogen?
Don't do that.
You were serious?
Okay, you made it easy.
Alright, go, yes.
You did not make it easy.
Bars,
Yeah.
I'm a big Dodd fan. I'll take them. I'll take them reluctantly, how about that? If I put a frowny face on your test, then you'll know why. Okay, go, 12 seconds.
No, carbon has 4. Yeah. Oxygen has 6. Hydrogen has 2 in this problem.
So I'm not sure exactly.
Hydrogen only has
It doesn't matter whether I put it here or here. Okay, cancel out the electrons from this guy, then it has to go.
2 hydrogen.
You can't cancel out the electrons here, it could go over here.
That's why you had to grab
Did you get all your atoms?
I did it wrong.
Did you get all your atoms?
I have 8 left. No, I don't.
How many?
I have 4.
Well, that was step one. Did you do step one? Was that right?
Okay.
That's right.
All the rules.
How do you get all your
Find the central atom. You put all the others on the.
I think you use like this. I use these, and I have these. Right.
Okay, then carbon on the other.
I did see, and then do from the, and then he did.
You don't have any more, what do you do?
Like he did up there.
What did you do?
Which you got your hair around. This is the exception, those are the, so you have 2
I
from
can only get two.
Good. Thank you.
I'm not saying I'm fine. You're surprised?
No, I put a bond where there was nothing there. So I had 2 electrons left over. And then you shared. I had it right before. It's not right.
Now, in truth, what you should do is erase those, even though I see what you're doing.
It's
but it
notes
looks-
though. I'll put a note in there to erase.
All right, should we do it together, or you want me to just put the answer up?
No, do it
Do it
together.
together.
Let's do it together. So how many valence electrons do we have? Hydrogen?
2.
Well, there's 1, but there are 2 hydrogens, so there's 2 total. Carbon,
Four,
oxygen,
six,
total.
12,
Okay, central atom.
carbon.
It's always carbon if there's a carbon, right? Step next.
Put the 4.
Bond all the other guys to the central atom with a single bond. So how many electrons did I use? Got 6 left. What's the next step?
I don't understand what's going on fully also.
You have to connect each one of them to the.
I understand that, but
Then you have to go
the way he did it
with
confuses me.
Because I'm following the rules. I'm following the steps as they're outlined to get a correct dot structure. I'm not making up my own rules. I'm not going to put 4 because it has 4 to start with. I'm giving him what the instructions tell me to give him.
Got it. I got it now.
All right, we're clear?
Yeah.
So now, how many have I used on the oxygen? Another 6, so I have
0 left.
0 left. Is everything good? Is everything copacetic?
You need to make the oxygen.
Carbon is deficient, so I have to,
Yeah.
hold on.
So we have to put the oxygen on top and 2 hydrogens on top.
Turn your head and see if that looks the same. Right?
No?
It'll be fine. Yes, ma'am.
We don't have octets on every one of them.
We do, except for hydrogens, which have a duet rule.
Okay.
Remember, hydrogens are special. They don't need an octet, they need a duet.
Hydrogen should have duet.
Yep. All right?
That was what.
I should have more. I suspect there's more on the website somewhere. But I'll do so. Rephrase what?
Can we do
All the
N?
rules? Well, I would do just what it says. Yeah, I think that's what we're doing.
Can we do NCl3?
Yes. We've had a request for NCl3.
Like that.
So, step 1, here, I'm getting rid of this. Step 1, number of valence electrons. So nitrogen,
5,
chlorine,
7.
7, but there's 3 of them. Total, 26 to play with.
Yeah.
All right, let's pick a central atom.
Nitrogen.
Pretty clear. Next step,
Bond here.
single bond all the others to the nitrogen with a pair of electrons.
Okay. None do.
Could I put them on the bottom? Yes, you could have put them on the bottom if you wanted to. All right, what's the next? Oh, how many have I used?
6.
So I've got 20 left. So what's the next step?
Outer bond.
Outer arrangement. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have 2 left.
I can't see your dots.
Put them on the
Dots are very
nitrogen.
hard to see. Thank you.
No problem.
Okay, done deal.
Okay, so I've used 18 of my,
So you got 2
no, I've used 24 of my 26 electrons. I have 2 left. And I need them on the central atom. And now, who asked if we would have an octet at one point? There it is. No multiple bonding necessary.
So it's perfect.
It's chemistry, of course it's perfect. Then we would cry. Okay? Is that a real possibility? Yes, and we will avoid those like the flu. Okay? Because those create what we call free radicals. And they're a special group of compounds that are beyond our scope.
They're not gonna be in any test we have.
Nope. Yes, ma'am. Yes. Should we do one?
Yes, please.
Okay, the question was, do we have to do polyatomic ion structures? And the answer is quite possibly yes. So let's try our rules on this one, see where it gets us. So what's step one?
Hang on.
Valence electron. So sulfur, oxygen. But there's 4 of them, so 24.
Plus 2.
A -2 charge
Plus 2.
means we have another 2 electrons. So we have
32.
32 electrons altogether. Very good.
Because 24 plus 6 is 30.
Okay, central atom. Sulfur. Next step.
Then put your oxygens around that 4.
Oh, we already have an octet.
4, okay. So he's
I've used
8.
8. Leaves me with
20.
it is higher math, I know.
It is.
We do have calculators. Okay, 24. Now what's the next step?
Do the outer round.
Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24.
That's an amazing stuff.
I have 0 electrons left. Do all my oxygens have an octet?
Yes.
Does my sulfur have an octet?
Mm-hmm.
Am I going to put a -2 charge nearby to indicate that this is an ionic particle?
I suppose.
That would be nice. And I'm there.
Done. Done deal.
Not so bad.
So we have,
Yes, ma'am.
okay, so if on the test, we need to put diamond particle, but everything else is right when we still.
I'd probably take it. I'd probably take it. Okay.
More?
Do
Let's
the,
go. Let's go on because we'll be doing some more with the next discussion of stuff that we have to talk about.
toys.
So, toys. Okay.
You both look like little Eskimos.
The shapes of molecules are important to us. It's hard to understand right at this moment why that's the case, but they are. When we get to another topic later on this semester, namely solution chemistry, we're going to want to know something about the shape of the molecule that we're dealing with, because it gives us a very important property about them. Now the Lewis dot structures are good, but they're always flat. We're always drawing them on paper or on the board, and so they don't look like they have any three-dimensional structure to them. But in fact, we know that molecules are three-dimensional. So what we have to do is sort of make the transition. We have to translate. How do I go from the two-dimensional picture here to what this thing would really look like in space? I need to know its complete geometry, its shape, if you will. Now, we can tell a lot of structures by simply considering a very simple process. Again, sort of a stepwise type of thing. We look at the central atom. The central atom appears to be central in all of this. Okay? So we look at the central atom, and we ask the question, how many electron groups are around the central atom? Now, what's an electron group? An electron group will be a pair of electrons. Okay, a lone pair of electrons, or a bond. A bond counts as an electron group. A double bond counts as one. electron group. A triple bond counts as 1 electron group. Now I think, haven't read the book in a while, but I think in your book they make the claim that you count the electron pairs, which is very misleading. Because if you have a double bond, it's got 2 electron pairs, but you really only count that as 1 group. So I use the term electron group. So we're going to look at our structure and say how many electron groups does it have. All right? And then from there, we try to determine what the shape of the molecule should be. So let's consider it step by step. Suppose I have, how about carbon dioxide? All right? So what we have to do here is do the dot structure for carbon dioxide. So you see we're going to get more practice here. So let's use our stepwise process to do this. Carbon?
4.
4. Remember, it's valence electrons, not total number of electrons, but valence electrons. Oxygen?
6 times 2.
6 times 2, 12 total. 16. Central atom? Carbon. Next step?
Oxygen's on the outside.
Okay, I'm going to put the oxygens on there with a single bond. How many have I used?
4.
Got left?
12.
12. Next step?
Outside.
Fill the outside guys. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used all 12. I've got no electrons left. Do I have my octets?
No.
So something's got to happen here. Multi-bonding. There. Does that do it?
No.
No. So does that do it?
Yes.
Excellent. We have the dot structure for carbon dioxide, CO2. Now, let's focus on the shape of this molecule. Look at the central atom. And how many electron groups are there?
2.
Only 2. Okay? There's 2 double bonds, but a double bond counts as 1 group. So there's a group here, there's a group here. Now, imagine this. Imagine that we're playing with electrons in string. And we take electrons and tie a piece of string to them and tie the ends of the string to one point, like a nucleus in the center. And we let them go. Now, electrons are what charge?
Negative.
So what do they do to each other?
Okay.
They repel. So when I let those 2 electrons go with their pieces of string, their leash, so to speak, they're going to try to get as far away from each other as possible. So what geometric shape will they map out if 2 electrons are trying to get as far away from each other as possible? It's a line. We call it a linear structure. So the molecule appears to us to be linear, like so. Okay. So now we have the 3-dimensional shape of our molecule. In the case where we have 2 electron groups, our structure should be linear. That's our conclusion. Let's move on. If we have 3 electron groups, okay, here's a good example. This exercise that we did right here, H2CO. When we finish this, look at the carbon. How many electron groups does it have? 3. It has 1 here, and 1 here, even though this is a double bond, counts as 1. Again, back to the electrons, tying with string. I got 3 of them this time that I'm going to tie to a center point and let them go. What figure will they map out in space, trying to get as far away from each other as possible? A triangle. They're going to map out a triangle, a flat, in the plane type of triangle. So the shape of this molecule is actually what we call a planar triangle. If you guys wanted to use lines, we'll use lines. There. There's my structure for that molecule. And it's a planar triangle. It's flat, like in the board, and it's got a triangular shape to it.
So in that structure, carbon dioxide would look like 2 lines in the O.
Yeah. We would draw it like that. Right, as long as you remember that a dash or a line represents a pair of electrons.
Okay, so even though you've got two groups, there's two groups of two. So you have two lines on each side.
Well, the lines represent the bonding, not the electron groups. Okay, electron groups is a separate consideration.
I understand that.
So this counts as one electron group, one electron group. Two electron groups on the carbon, the shape must be linear.
So you only draw lines for group,
Draw lines for,
group, you don't draw lines.
no, I'm drawing them for bonds. I'm not drawing them for groups. Okay? One line is a pair of electrons. And so instead of drawing 4 dots here, which is 2 pairs of electrons, I can just draw a double.
But you don't draw a line for the outside here.
I don't draw a line for the outside pairs, no. We basically can't see them.
Yeah.
Well, I think I called it planar triangle or trigonal planar. There's a couple different terms you can do as long as you get the right descriptors in there to show that it's a flat, in the plane triangle.
I understand what he's talking about.
Okay?
I'm sorry, something 117.
Let's try methane, CH4. I think we can do this without our rules. Okay? Let's live on the edge. Now let's try this without our rules. Who do you think is a central atom?
Carbon.
And how many valence electrons does he have? 4. So I'm going to put those around the carbon like this, and then ask where would I put the hydrogens?
Each one around.
Like so, right? Now, if we followed the rules, do you think we would come up with that structure?
Yes.
Yeah, we sure would. It'd be pretty easy. Okay, let's use that as our example here. We have a central atom, which is carbon. How many electron groups are on the central atom? 4. So we're moving up in the ranks here. We've done 2, we've done 3, now we've got 4. So I tie 4 electrons, little pieces of string, to one point. Let them go. What shape do they map out? It's not a square. In 3-dimensional space, it's a tetrahedron.
What is a tissue?
I'm glad you asked that question, because I brought my visual aid. This is a tetrahedron. Notice the 3-dimensional shape to it. So in other words, these two guys are further apart from each other than they would be if they were in a square, in which case they would be at 90 degrees. You can see that this angle is greater than 90.
It's a tripod.
No, it's a tetrahedron. All
See,
right?
now it's a tripod.
So the shape of this molecule is tetrahedral.
Can you spell that?
I can, spelling it correctly might be a trick. So, tetrahedral. Okay,
But were you able to draw it?
were I able to draw it?
Or will we have to draw something?
I can attempt to draw it. It always leaves a question because you're in 2 dimensions. The more important thing is, do you have it in your mind as to what it is? Now, I'm sorry, but we can complicate this problem.
Of course it goes.
Okay?
Pretty well that long.
How can we complicate the problem? We can complicate the problem by this example right here. NCl3. Let's analyze it. Central atom. Nitrogen. How many electron groups?
4
4. So the shape would be
tetrahedral.
tetrahedral, right? But here's the complication. When I'm looking at this molecule, I can't see these guys. They help in the formation of the shape, but I can't really see them when I'm looking at the molecule, because there's no nucleus here. See, there's a nucleus here, and here, and here, and here, but not here. So what we have to do is ask the question, what would a tetrahedral shape look like if you couldn't see one of the extensions? It looks like a triangular pyramid. See how this is not down on the table? It's up, so it's like a little pyramid shape. So the shape of this guy is triangular pyramid. Did you spell that right?
Y-R-A-M-I-D.
Triangular pyramid. So these take a little bit of getting used to. Okay, you've got to look at the different cases and say, all right, what am I actually looking at? Yes, sir?
So would you draw a line without another letter there?
I would not.
Or you would draw a line without?
I would not. So the structure actually looks like this, where the brown sphere here is that lone pair of electrons. And so imagine that you don't see the brown sphere. So what you're looking at is a thing that has a triangular base, but is lifted up off of the surface, and so it's a pyramidal pyramid type shape. Triangular pyramid for our NCl3.
So you said it would be triangular instead of the tetrahedral because we can't really see the other.
I can't see one of the extensions.
Okay.
Okay,
I have a
so
question.
boom, that's what it looks like. Yes.
Okay. The triangular pyramids. So you're telling us if we were looking at the shape of it, we wouldn't see the last two at the bottom.
Correct.
So if we had to draw the Louis structure and then name them, we wouldn't name them a because we know we put two dots.
Well, you don't name dots anyway,
Okay.
so
Okay.
I don't think that would cause you a difficulty if you were naming it. The only difficulty you would have is if you're trying to explain the structure and you're visualizing the electrons when you shouldn't be. Does that make sense?
But how, so when would we know to call it a triangular, the other one, the planet? Yeah, how would we know which one to call it? If it was a pyramid or?
Okay, that's a good question. How many electron groups do I have here?
Right.
What is the shape of a 3 electron group?
Triangular,
Triangular, planar.
planar.
Okay. How many electron groups here?
Four.
4.
Okay, got you.
Okay, and that leads to tetrahedral, but tetrahedral without one of the arms is triangular pyramid shape,
Okay,
not planar.
okay.
Better?
Yeah.
All right, let's, yes, ma'am. Are we good? Oh, I thought you were talking to me. All right. Let's do water.
What?
We need a dot structure. Do the rules or not rules? No rules, let's just do it. Oxygen, how many valence electrons?
No, oxygen, 6.
All right, you think we could figure out where the hydrogens go?
Mm-hmm.
Like so? No?
Yeah, you can.
Thank you, appreciate it.
Oh my gosh.
All right, let's look at my central atom, which in this case is oxygen. How many electron groups?
4.
Electron shape. It's a tetrahedral,
Yeah,
right? I got 4. It's tetrahedral.
but two of the arms are not showing.
But 2 of the arms are not showing. So let me remove 2 arms. And what shape do I end up with?
A V?
what we call a bent shape. Okay, it's a V.
How on this is arms not shown?
You don't see the electrons.
Because it's not
So when you're
completely-
looking at this tetrahedral, these two segments are not visible to us.
Okay, if they're not.
So it's like pulling off the two arms and we see what's left, which is a bent shape.
So we don't, if we're not, if we don't follow tetrahedral.
It depends, okay? You have to read very carefully. Because what is the electron group shape? Tetrahedral. What is the molecule shape? It's bent. So you need to read very carefully. Is the question asking you about the electron groups, or is the question asking you about the molecular shape? In which case you're only describing the atoms that are there.
So that goes
So
the
you-
same.
Go ahead.
So that goes the same for the triangular pyramid.
Yes, it would be a tetrahedral electron group shape. It would be triangular pyramid for the molecular shape.
So you wouldn't be able to put this as a linear, where you put the H on the other side?
I could put the H on the other side because I don't have a rule that says it has to go here.
Okay,
But remember, the picture that's on the board is not necessarily the shape of the molecule. Okay? In other words, what if this is where the hydrogens are? Okay, now watch. If I tip it this way, how would that look to you?
linear,
It would look linear if it were flattened out.
right,
But it's not flat. It is a bent shape.
I got you.
So that's why we have to go through the whole liturgy here of
Okay.
what is the shape of the molecule. Yes, sir.
Here's the name of CO2, the shape of the molecule.
Linear.
Because it's straight across, like a line.
So what was that? So it's not part of the-
Bent. That's what we call it. Bent.
But what keeps you from putting? I'm sorry.
Hold on.
So if we were to draw this, you would just draw the O and then oxygen, I mean.
Yeah, if you were trying to draw this with some regular structure to it, you would probably draw it like this.
And you don't include the other dot.
We don't. You could, but typically we don't. After we've gone through the business of knowing that they're there, then we don't see them anyway.
Okay.
Now, you bring up an interesting point, and that is the angle that's here. The angle of a tetrahedron is 109 degrees, 28 minutes. No, you don't need to know that. 109 degrees, 28 minutes. But when we pull off an arm, because there's a lone pair of electrons there, those electrons actually force these guys closer together. So the angle for water is not 109, but it's more like 104 or 105. We don't need to know that. We just need to know it's a bent structure. Okay. Yes, ma'am.
So when you have two electron groups, it's linear.
Yes.
Three, the triangle one has four, it's tetrahedral. The electron group shape.
Yes.
Okay.
Yes. And I'll tell you what, we won't go past tetrahedral.
Oh, okay.
Are there things past tetrahedral? Yes, there are. And if you were in the majors course, Chemistry 1211, you would be going on to some of the more difficult cases. We'll stop at 4 because there's enough complication with that. Now, let's go back to, do you remember, didn't we do an SO2?
Yes.
What, look back in your notes real quickly, what did the dot structure look like for SO2?
It was linear. You have 4 on the left of the S and none on the bottom of the H. Of the O.
Okay, so did it look like this?
Yes.
All right, let's analyze this. Central atom,
So,
how many electron groups?
3.
Shape that it would have?
Triangular pyramid.
It would be a planar triangle for the electron group shape, right? A planar triangle with the sulfur in the middle here. But this is a lone pair. We don't see those. So what is the molecular shape? It's also bent. we would come to that same conclusion, that it's bent.
So the electron group shape is the planar.
The electron group shape is the planar.
Okay.
The molecular shape has to account for the lone pair of electrons that we don't see.
So you basically like try to figure it out based on the signature.
It's always the central atom that you consider, absolutely. Yeah.
So the M shape and the group shape are always different.
Not always. The electron group shape here, tetrahedral. Molecular shape, tetrahedral. There's no lone pair to disrupt things. Okay? Carbon dioxide, electron group shape, linear. Molecular shape, linear. Doesn't upset things. This one right here, electron group shape, triangle. Molecular shape, triangle. So it's only when there's a lone pair of electrons around the central atom, so there's no lone pair here, that we have an adjustment to make to the molecular shape.
Oh, okay, so the SO2, there's a, okay, got it. Got it. Got it.
All right? How many people are totally confused? How many are just slightly confused? How many are not confused? All right, it's not bad for the first time out of the box.
So what was the difference in that being linear from a line to make you having to make it feel
Who?
the just like you only had two that was visible.
Which molecule are we talking about?
Yeah, that's what you.
SO2? Okay. Why isn't it linear? How many electron groups are around the sulfur? Three. And 3 would be triangular, not linear. And triangular with one of the spots not being seen would be a bent structure.
So you just have two atoms. That's still linear.
Yeah. In fact, we could get a little bit more complicated with that. But you'll see it's not a complication. Let's do HCl. Okay? I don't think we have to do the rules here. Let's just do HCl. Chlorine has what? 7. So 1, 2, 3, 4, 5, 6, 7. Is it clear where I'm going to put the hydrogen? All right.
Aren't you missing the L? Missing the L?
I am. Thank you. So, what do I have here? Chlorine, central atom. How many electron groups? 4. What would its electron group shape be? Tetrahedral. But if 3 of the arms are missing, it's going to be linear. So basically, when you have 2 atoms, it's got to be linear. You've only got 2 points. But this works. This is a linear shape, even though it came from a tetrahedron, because we're not seeing 3 of the sides. Tetrahedron will be linear if you have just 1 atom attached and 3 lone pairs, yes. All right, questions? Yes.
When we get test review.
You can start reviewing tonight.
Oh, yeah, or I mean, like, we have.
Sure. Absolutely.
Is there any names we're missing out of the 4? Just 4? I got linear, bent, triangular, planar, triangle, pyramid.
I think you're good. I think you're good. Just keep in mind that a electron group shape and a molecular shape are different, or could be different. They could be the same. They could be different. All right? And then you'll be all right. So, probably a burning question in your mind right now is, why are we doing this? Why do we want to know the shapes of molecules? There's a very important property of molecules that we need to be aware of, and it has to do with the result of the shape. So, to understand this, let's drop back a little bit and go back to ionic bonding. If I have NaCl, how did that come about? You wanted review? Here we go with a little review. NaCl, what are we talking here?
Sodium chloride.
Sodium chloride, and so what has happened in this structure? We had a chlorine, how many valence electrons? 7. And sodium, 1. And so what ends up happening here? Share?
They transfer.
It's a transfer, right? The sodium says, take it. I don't want it. And becomes a sodium ion. The chlorine says, absolutely, I'll take it. And becomes a chloride ion. And then the positive-negative attraction is what we call the ionic bond. A bond made between two ions. Seems to make great sense. Okay? And what was the opposite of this situation? What these two guys do? They are the sharers, right? We drew a hydrogen, and we said, let's draw another hydrogen. Look, they will come together and share the electrons. It's a warm, fuzzy feeling that they get from each other. Okay? We have sharing. This was ionic. This is covalent. Okay? In fact, this is what we call perfectly covalent. Why perfectly covalent? In your mind, would either one of these hydrogens have a stronger preference for the electrons than the other?
No.
They should be exactly the same, right? They're both hydrogens, they're both identical. They should have the same attraction for those electrons. But if you look back in your notes, I think you'll find out that we did this. Both those guys have 7 valence electrons. I put them together with a single bond, covalent bond, but is it perfectly covalent? Or in this case, do you think one of those guys might have a little stronger pull, a little stronger attraction for those electrons in the bond than the other guy? Yeah. And so here the electrons are not shared equally. They are shared unequally. In other words, one of these guys is going to have a bigger share of the electrons. Now we can think of this in a lot of ways. One way, you could think of the electrons as a cloud here, forming in the center. And the cloud would have a shift towards one of the atoms more than the other. So the fog or the density of the cloud would be greater around one atom than it would around the other. Another way to think of it, maybe the better way for us, is to talk about time. Time share. Each atom has these electrons 50% of the time. Right? Let's think of a divorced couple, and they've got a kid. Could they share the kid 50-50? Yeah, 50% of the time at mom's, 50% of the time at dad's. My wife and I are both from Chicago, and our families live up there. And by God, when we go up there for a holiday, 50% at her house, 50% at my house, or there's hell to pay. You know what I'm saying? Okay, so they could share perfectly. But does the sharing have to be perfect? Could the sharing conceivably be 60% on one and 40% on the other? Could it be 70% on one and 30 on the other? 80 and 20. Okay? Could it be 100 and 0? Yeah, except in that case, we're probably not talking sharing, we're talking a total transfer, an ionic bond. So what are we saying here? Lots of flexibility for the sharing of these electrons. We have a little symbolism that we use to show that. The guy that gets the electrons more, we use a Greek letter delta, which looks like sort of a squiggly S, and a minus sign to indicate that it's partially negative. And the other guy is partially positive. So the Greek letter delta means partial. So I'm not trying to say, hey, there's a transfer of electrons here, like we said before. I'm saying that they're basically sharing, but they're not sharing the same. One guy has a little stronger pull for the electrons than the other guy.
How do you know which one would be the electron?
Excellent question. I'm coming to it. I'm coming to it.
Wait, the negative means it
I'm
has
gonna ask
no.
you, what was the names? I know you said ion and something.
Ionic and covalent?
And why is that transferred?
Well, if I put the sodium here, then the sodium doesn't have an octet. Okay? So what he really does is he gives it away, and then if you look on the table, he goes back to being like neon, so now he does have an octet in the previous shell, because he gave that one electron away that was in his outer shell. Yeah,
So the delta negative means
it's a little bit negative.
it's like negative.
Delta
Okay.
positive means it's a little bit positive. Not a full positive, not a full negative, but a little bit.
Does placement on the periodic table determine which one is stronger than the other?
Yes?
Is that because I'm thinking ionization energy?
No?
No?
See, look at you guys, you're so eager to get on with it. All right, I'll tell you. Wouldn't it be great if we had a property that measured an atom's ability to attract electrons in a chemical bond?
Oh, we do.
We do. And it's called big word, electronegativity. Electronegativity is defined as an atom's ability to attract electrons in a chemical bond. Now, wouldn't it be awesome if there was a trend in the periodic table that told us something about electronegativity? Remember that table we made in your notes? We left a blank space. We left it for electronegativity. Is there a trend in electronegativity? Absolutely. What is the trend?
What is the trend?
As we go from top to bottom, electronegativity decreases. As we go from left to right, electronegativity increases. So if we don't count the noble gases, because they typically don't form compounds anyway, who do you think is the king of electronegativity? Don't count the noble gases. It's fluorine. F. Fluorine is the top guy. So that's why he's getting the little negative sign here. Because he's pulling those electrons a little bit closer to himself than the chlorine is able to pull toward itself. So, do we have a name for this? Well, this was ionic bond. This was covalent. This is called polar or polar covalent. If you're going to call this one covalent, we could call it perfectly. Perfectly covalent. This one, polar covalent. And if it's polar covalent, it sets up these different charges. This creates what's called a dipole moment. We often symbolize the dipole moment with an arrow that has a little plus sign on the side that's more positive. So it's a feature of the molecule that it has this dipole moment, or actually a feature of the bond is where we're at. We're talking about a single bond here. And so this is a polar bond. Now how am I going to tell when the bond is polar and when the bond is not polar?
When it's not the same.
The true definition is if the two atoms have the same electronegativity, it would be nonpolar. If the two atoms do not have the same electronegativity, then one has a stronger pull, then it's going to be polar. Okay? Now, how am I going to know that? Am I going to memorize every element's value for electronegativity? We're not going to do that. But we have a trend in the table that will guide us. Okay? Now, granted, we're going to be wrong sometimes. But the bottom line is this. If the two atoms are not the same, what's our guess? Polar. If the two atoms are not the same, we're guessing polar. Now, we will fail. If we looked at carbon and sulfur, for example, If you look on a table, you'll find out they have exactly the same electronegativity. But if we saw carbon and sulfur, what are we thinking? Different atoms, therefore polar. We'll live with those few mistakes, okay, to make it easy for us to guess. Perfectly covalent is always nonpolar because it's an equal sharing. There's no polarity associated with it. And when do you have perfectly covalent?
With the Huckleberry?
When the two guys are the same, Hankelbrief, okay? Now, in truth, it's when the electronegativities are the same, but the only time we will know that for sure is if the atoms are the same. So that's going to be our guess. Same atoms, perfectly covalent, nonpolar. Different atoms, polar. Okay? Now, the other thing we need to consider is the degree of polarity. And that varies a lot because it varies on electronegativities. If the two electronegativities are very close to each other, then the degree of polarity is very small. If the two electronegativities are very far apart from each other, then the degree of polarity is very strong. A good analogy here is refrigerator magnets. Okay? I believe it's a state law in Georgia that you must have refrigerator magnets on your refrigerator. Now, are all refrigerator magnets created the same? No, you get that free one in the mail, and what happens? You put one piece of paper up and boom, it falls down, right? But you go to the dollar store and buy some that what? You have to use the jaws of life to get them off your refrigerator because they're stuck so hard. So, like refrigerator magnets, bonds will vary in the degree of polarity. And that will have an impact on what we're going to talk about next. I'm seeing that my time must be running out because people are packing up their books. So, what was the last statement I made? Bonds will vary in the degree of polarity based upon how big of difference there is in electronegativity. All right? So on Thursday, we should finish this chapter, and we should probably consider our next exam, which will not be next Tuesday, because it's a holiday. It could be next Thursday.
I go to Walmart.
We'll go.